Okay, so the last video I made did not record the audio properly, so it was corrupted about halfway through, so I have to basically go over all of this again. I'm not going to rewrite it all just because it's a lot to rewrite, but I'll talk about it all. So we're talking about vector potentials. So recall that for a complex vector, so it's an element in the spacetime algebra that has grade 1 and grade 3 components. When you take the gradient of that, it's in the even subalgebra. And so if you have z is equal to this, where a, e, and am are vectors, then when you take the gradient of that, you get grade 0, grade 2, a grade 4, and a grade 2 component. So if you want this to be the potential for a bivector field, that means that you want the gradient of z to only have bivector components. So these are not bivector components, this is not a bivector component, so these are set equal to 0, which means that this right here would be your equation with the potential representation here. So this condition that we came up with because of the geometry, because this is not grade 2, this is not grade 2, this is called the Lorentz gauge condition, and is something that is traditionally imposed for different reasons, but we did it because of the geometry of the space. Now, to find a solution for z, it's useful to recall the solution for the monochromatic solution for f, where we have a single color. And so we'd like to consider what happens if we don't have k down here, but we have I and s. Well, it turns out that taking the gradient of this, it doesn't affect is, it only affects this. You have a factor of ki come down here, which equals negative ks equals sk, which is just the definition of f again. So that tells us that indeed is e to the k dot x I should be the monochromatic potential. But again, this is monochromatic, so it's not polychromatic. So let's move on to polychromatic potentials. So if you have f, which is polychromatic here, then that implies that your z will be like this. The paper says that the gradient of alpha minus gives a negative sign, so there's a negative sign here for that. Although I'm not sure, I don't know about that, but uh, just that's why that needs to be there. They don't give any proof or something, and because there's such little information given in the paper, I can't prove it myself, but this is what's there. And the reason why we have a factor of c over omega here is so that this omega over c cancels with it, and this s here will then contain the magnitude of an omega over c, whereas in this thing, the s doesn't contain that, so k contains it. But that's basically like saying, so s k is equal to omega over c s k naught, and the difference is that when the authors used the s here, the s did not contain omega over c, but when they're using it here, it does contain it. So this s here is equal to s times omega over c. It's a little confusing, but that's what they did. Now for the superposition of all plane waves, this is the field f, the bivector field, and then you just want similarly to not have k present down here, so there's no k, and you divide by the magnitude k because there is a factor of k in all these alphas. So when k comes down here, you want the magnitude of k to cancel with this magnitude. So that's what happens here. So you can break these into relative frames. So here, I'll zoom out so you can see all of this. Then relative frame of vector potential. You can break these into both their relative frames, which allows us to rewrite the Lorentz condition. And so you just have that these are the scalar parts. These are equal to 0. So if you take a spacetime split of f equals the gradient of z, then you take the spacetime split of each individual part, and then you multiply through. You end up with all of these different terms, and then all of the terms that are equal to the divergence up here, those go away. So this goes away, this goes away, this goes away, this goes away, and you're just left with this, which implies that the electric and magnetic fields are equal to these potential representations, which is what they are in traditional electrodynamics. So that's how they can be derived in the spacetime algebra. However, in traditional electrodynamics, there is no magnetic charge, so there's no magnetic potential, so this is zero, and this is zero. So you'd traditionally only have E equal to this and B equal to this.